What's up, y'all? I wanted to talk about the double-slit experiment. So I thought we would start off by maybe just watching some videos on YouTube where they explain the double-slit experiment, at least our current interpretation. I'll just provide links as I go.
I'm going to explain to you what's known as the central mystery of quantum mechanics. It was Richard Feynman, the American physicist, said, this is the central mystery of quantum mechanics. There's lots of weird stuff that goes on in the quantum world. Hit you with this, and it basically tells you what it's all about. It's called the Toothless Experiment. I'll start with this. Imagine you have a source of light shining against a screen with two slits. Now, for the pedants in the audience, this source of light has to be monochromatic light of a particular wavelength, whereas, of course, a light bulb is white light, and that's made up of all the colors of the spectrum, lots of different wavelengths. But imagine this is just a single wavelength of light, and you can see the light is coming out in waves like ripples in a pond. That's the nature of wave-like behavior. As the light hits the screen, it squeezes through the two slits, and each slit in turn on the other side becomes almost like a new source of light, and the light spreads out, it diffracts. And as the waves of light overlap, they will interfere with each other. So where a crest hits a trough, they will cancel. Where a crest hits a crest, they will amplify, and so on. And so on the back screen, you end up with what's called an interference pattern, a series of light and dark fringes, where the waves have either cancelled out or worked together in phase. That's fine. That's not quantum mechanics. That's a property of light that goes back over 200 years that we've known about since the early 19th century. Imagine doing the same experiment again, but doing it not with waves, but with particles. Do it with grains of sand. So this is the same experiment, but I've tipped it 90 degrees. Rather than waves that are spread out that wash up against the two slits and squeeze through, here you've got individual particles of sand, and each particle will either go through one slit or the other. And so you see they will sort of drain through, and you get two bumps underneath each of the slits. So the two peaks is reminiscent of particle-like behavior, whereas the multiple pattern of interference is wave-like behavior. What if we do the same experiment with atoms? Well, so imagine we have an atom gun, something that can fire atoms, a stream of atoms. You can't see them because they're very small. Let's block off one of the two slits. So these two slits are the dimensions and separation of the slits is chosen appropriately to show us how atoms do things. And so far so good, nothing strange here. You'll see a lot of atoms hitting the back screen. So this will now have to be some sort of photosensitive screen whereby when an atom hits it, it'll give off a little flash of light to say the atom has arrived here. So the atoms are arriving as these little pinpricks of light that we see. Of course, a lot of the atoms will be blocked by the first screen. They won't go through that slit. But those that do get through to the other side, you can see there's a bit of spreading of the atoms. But if we didn't know anything about atoms, we'd say, well, that's fine, we can understand that. A lot of the atoms are going clean through the slit. Some are sort of maybe bouncing off the edge of the slit, and so they're sort of being deflected a bit, which is why you get a bit of a spread. The first mystery of quantum mechanics comes when we open the second slit. Because now we see something that's very much like the interference pattern we got with light. Rather than having two bands of spots where the atoms have gone through the two slits, it's as though the atoms have gone through the slits behaving like waves, and you get interference of the waves and you get these bands. If we know nothing about atoms or quantum mechanics, you could try and rationalize it and say, well, maybe atoms behave in a very strange way, and only a certain number of them are allowed to all sit together. And so, me and my gang, we're all going to go on this slit. No, sorry, no room for you. You go to the next slit above. And by the way, there's this rule that no one can go in between the two bands, but a few naughty atoms do. So there's a bit of a scatter. There could be some forces between atoms that make them coordinate their actions in a way to give this pattern. That's not mysterious. We just don't know how atoms do things. But we can be clever, and we can force the issue. What if we were to not send the atoms all through at once, but send them through one at a time? Leave enough of a gap for the atom to get through to hit the screen. Of course, as I say, some atoms will hit the first screen and not get through, but those that get through will hit the back screen. So let's run the experiment again slowly, and gradually you'll see as the atoms go through, they'll be look like they're just randomly arriving on the other side. You keep sending atoms through one at a time, and gradually that same pattern appears. So each atom by itself is somehow contributing its small part to the overall wave-like behavior that we see in the interference pattern. How does it do it? We know the atom's a tiny, localized particle. We can't see it. It's too small to even see under a microscope. We're firing it at the screen with the two slits. Some moment later, you see a flash of light on the back screen. It's arrived in a localized point. It's not spread itself out. You don't get sort of like a wash of sort of a faint light across the whole screen. It's a little point. The atom is localized. It's arrived in a certain location. And yet, it somehow seems to have been aware of there being two slits, not one, because it's given rise to this interference pattern. How does one atom do that? Does it split in half? Does it become like a cloud that goes through both? Well, we can try and be even cleverer. What if we were to spy on the atom and see where it goes? We can gently just observe which slit it goes through. So you put a detector just above the upper slit that will flash or beep whenever it sees an atom go through that top slit. Sure enough, you fire the atoms through, one at a time. 50% of the time, the detector will beep. The other 50% of the time it doesn't, the assumption being that the atom has gone through the lower slit. But of course, I've been cheeky here. I haven't shown you the results of the experiment. That's what you get. 50% of the time, it beeps, and you see a spot arrive adjacent to the upper slit. The other half of the time, it doesn't beep, but you see a spot arrive at the lower slit. So, yeah, it's picked out the atoms that have gone through the upper slit and not the ones that have gone through. So each atom does go through one slit or the other. But that's a different result to what we had earlier. So here's the last bit of sneakiness that we can play with atoms. Surely now, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment. Atoms, okay, get ready, one at a time. We're going to be checking on you. All right, so run the experiment again. Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you. Quantum entanglement.
Okay, so he was talking about atoms, which also apply to this experiment. So let's go back. So the double-slit experiment is intriguing from a physics perspective because the thought is that if light is composed of particles, then it would produce a particulate pattern like this one, like this. And it doesn't, so we're like, therefore it's a wave, and then we observe it like this, where we basically try to detect which slit a particle, if it's a particle, goes through, and we detect a particle going through the slit. But what happens then is it produces a particulate pattern. And so, like he's saying, then when we turn off this detector, then it turns into an interference pattern again. And so what is not being mentioned is that this slit, the slit walls, the material that this component is made out of, where the slits are made, is a material that has a force of gravity that is inversely proportional to the distance of separation of that to whatever. And so if there's a particle passing through this slit where the slit is narrow, because we make the slits narrow in order to actually produce an interference pattern, we narrow the slits, which is why they're slits and not wide gaps. And in so doing, when a particle passes through the slit, it's either going to pass down the middle and continue straight, or it's going to be off center, and then it's going to be closer to one of the walls of the slit. And so inverse radius squared function of gravity, if the radius is small enough, and because it's a squared function, it's exponentially larger. And so when the radius shrinks, the force of gravity exponentially increases. And so when there's this small distance of separation between essentially the atoms of the slit material wall and the passing particle, then the force of gravity I'm supposing could be substantial enough that it deflects the particle. So the further off center it is, the more it's deflected, producing basically a wave. Like this. So when it goes down the middle, it's not deflected. But when it goes off center, it's deflected, and the particles that pass closest to the wall are most deflected, leading to the observation of the collective summation of all of the particles that pass through a slit as being a wave. And then when we use a detector, we literally put energy into the environment of the slit. And so perhaps what's happening is that because the environment is more energetic, there is a less of an overall force, because like if the slit is in a vacuum, then there's essentially no gravity from the particles within the slit. But if it's in air, if it's just out in the open, then there's air within the slit. And so it's going to also have a gravitational force on the passing particles. And so the deflection from the cumulative forces of all of the particles on the system passing through the slit can be less than in a vacuum. And so if you then shine radiation into the slit, it may be that it basically causes the gravitational force to the sides to become less influential, to the point where it takes what was a wave and collapses it into like a particulate pattern. And so when we stop observing, i.e. shining radiation into the system and actually influencing the environment in the same way that the material of the slit plays a role, like there's this underlying assumption that the material has no effect on the experiment. So let's go check another one. This one's pretty good.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit.
So they're saying if you shine particles, it's going to create this particulate pattern, but it's again under the assumption that this particle, as it passes through the slit, is the force of gravity of the slit material itself is basically irrelevant. It's so insignificant that it doesn't play a role. It's essentially zero. But because the slit is so narrow and force of gravity is inverse radius squared function, it may be that we're just simply not accounting for a force that's substantial enough to play a role in the observations that we see in a tangible way, which is the force of gravity of the slit material. And so it wouldn't produce a particulate pattern, it would produce a wave because of essentially the gravitational lensing of the particle as it passes through the slit.
Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern.
Assuming no gravitational influence of the slit material on the particle as it passes through the slit.
Of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe...
Unless waves are waves of particles, and this wave is being caused by the gravitational lensing of the slit material on the electrons as they pass through the slit, producing the collective effect of a wave, where then we see an interference pattern, even though it's composed of particles in a more like understandable and just like conceptually logical way, like classical mechanics.
Maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen.
Notice there's no consideration in this analysis to whether or not the slit material plays a role in producing the wave. And so by changing it to single photons and having the same result of a interference pattern, it's still possible that the reason is the same underlying reason as when we shine many at once. The same thing is happening, is that as they pass through, whether they pass through simultaneously approximately or with gaps in time, they're still going to go through some portion of the slit and then be deflected by the gravity based on where they go through the slit, and then the cumulative effect is still going to be an interference pattern.
Seem to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits.
The conclusion is inescapable. The single particle becomes a wave of potentials and goes through both slits. What I'm saying is that it's a single particle, just like Earth. Like, it's not suddenly splitting into two and being in two places at once, and then probabilistically doing some kind of wave function existence. But it's a particle, and that it's just being gravitationally lensed, producing a wave.
And interferes with itself.
The conclusion is inescapable, though. That it's just out of nowhere. That's the interesting thing about quantum mechanics. It's like our experiences day to day are basically classical in terms of like the laws of motion, the law of gravity. Like, things function where they are deterministic, where like a cup is going to remain a cup. It's not going to just shift probabilistically. At least, unless we got some like real deep, doesn't matter. It matters, but it doesn't make sense in the way that our experiences are solid. They're stable. Splitting in two, the conclusion is what do you say?
But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through...
So it becomes a wave of potentials, but then it recollapses to hit the wall. Or it remains one system, goes through one slit, is gravitationally lensed in some direction, whatever that direction may be, and then it hits the wall. And then when many of them go through, they create an interference pattern. It's logical, it's reasonable, and testable, where literally just changing what material the slit component is made out of so that its gravitational influence changes, and determining how that influences, if at all, the resultant distribution of light. Because if like, say it's made out of a light material like plastics or something like carbon based, then it theoretically would effectively have a lower gravitational influence on the particle passing because of its lower mass. And so like it couldn't create perhaps such a wide distribution of the passing particles. Maybe the wave it produces is only a portion as wide. But then if the material is high molecular weight, so like anything heavy, like iron based, like steel, then it would theoretically have a higher gravitational influence on passing particles. So when they're off center and closer to the slit wall, then the force of gravity is proportional to the mass of the material, and so it's deflected more, rather than with carbon, where it would just be deflected less. And so we could test it. And this experiment it's just not ever been done. But interestingly, let's see if this is it. Here it is. Turn off. Real-time single molecule imaging of quantum interference. The observation of interference patterns in double-slit experiments with massive particles is generally regarded as the ultimate demonstration of the quantum nature of these objects. Mind you, it may just be that gravitational lensing is always the cause of what we're observing, and changes in the environment and in the experiment are different ways. So like if a particle passes through the slit slower, so its velocity is lower, it's going to basically be within that small radius of distance of separation where the force of gravity is large enough effectively to actually cause lensing, because otherwise it's just in most of the distance of separation, like as the particle's approaching, its nearby environment is all uniform, so it continues moving in a straight line. But as it approaches this area where there's variation in the environment, it's not all the same. So there's mass on one side, mass on the other, and then high mass on two sides and low down the middle where it's going. Then it's going to be for a period of time at a small enough radius of separation where it may be lensed. And so if it goes slower and passes through the slit slower, then it's effectively going to experience that force of gravity for a longer period of time. So if it goes by real fast, it's just not going to be within that distance of separation for a very long time, so it's not going to be lensed. But if it goes through slowly, and so in certain circumstances, there have been experiments done where they took an entire molecule, this experiment, and shot it through the slit. But in order to produce a wave, an interference pattern, basically they had to make the slit small enough, and they had to make the velocity of the particle going through the slit slow enough that as it was in that slit region, the molecule could be exposed to the gravitational force for a long enough period of time where it produced a lensing effect, where the collective result was a interference pattern. But what's interesting about this experiment is they have to they have to do such a low velocity of the molecules. It's like they're lobbing them through the slit. And so as the molecules move, they literally move according to gravity of the earth, and so they start to actually fall. And so the slower the particles, the more time they have to fall. And so it basically separates them. The faster the particle, the faster it moves through the slit and hits the wall, the higher it is in the observation of where it arrives on the detector. And so it separates naturally the slower velocity particles. And so what happens is that the lower the velocity is, the more it fans out. And so the particles at the bottom of this image are more fanned out because they're moving slower, and so they're within the slit, small radius force of gravity of the slit wall for a longer period of time, and so they're able to be more deflected and affected by passing through the slit, so that their trajectory is more lensed, producing a widening of the distribution of the particles. So I'll stop with the videos there. I think they're all pretty much the same in terms of there's never even a mention of the possibility and the dismissal, the accounting for the experiment that basically got null results to prove that it's not gravitational lensing of the slit material on the particles as they pass through the slit. There's nothing out there to show that that's not what's happening. And so because it makes sense logically, I propose that that is what's happening and that we can test it. And that's the thing, is these experiments use really narrow slits, like nanometer scale slits. And to effectively test this, where the only difference is a different material is used, while the rest of the variables stay constant enough that their errors, where like the slit's slightly wider, say carbon has a slightly wider slit than a steel, and so steel produces a wider distribution, but the error of the differences in the width of the slit effectively makes it so that it's hard to decipher whether or not the material itself is playing a role, or if it's effectively that the slit was just narrower. And to get it with a small enough error bars, honestly, I don't know what to do. Like I'd like to try to reach out to some metal shops and be like, can you make materials precise enough to do this? Because I'd like to test this. I reach out to people, force my thoughts upon them. Please help me. Oh, God. But that, to me, is what's happening. Is that the material is gravitationally lensing the passing particles. And that's really the true and like crux of what is happening in this experiment that is so central, foundational, and fundamental in the entire way of seeing things, that is quantum mechanics. Again, I've said this before, I mean, there's definitely something to be said for quantum mechanics. to not completely be like, it's just classical and that's it and that's the end of the story, and like reality is infinite. It's just a different way of looking at the same system. And understanding quantum mechanics better, though, for sure would come through a classical analysis, while acknowledging there's something more than meets the eye to what's going on in this like quantum probabilistic side of reality. Anyway, if anyone wants to help me get this tested, getting the materials with the proper slit width, I'll probably end up doing it myself someday, if ever, and just moving along and with my life if not. But catalyst would be nice. Yay. Alright, so that's my take on the double slit experiment. Hope that was informative and insightful to some of the things going on with our interpretations and how they can kind of get like way out there in terms of like same. But peace out.